Good morning, ladies and gentlemen. May I have your attention, please? Thank you. At this time, I ask that you go ahead and check your bell work for today, September 10th. Raise your hand if you did not get a red mark for today. Everybody good? Wonderful. And so at this stage in our lives, we've got some tools for evaluating limits. We've got technological tools, which will enable us to evaluate limits numerically, right, or using a graph, or using our table set feature, zoom to enter, trace, things like that. And then we've got our non-calculator, our strictly algebraic methods, pencil and paper, where we're able to evaluate limits by using some different strategies that I'm going to have you share with the class in just a minute. So as I look at my first limit, we always want to try direct substitution first to see what we're dealing with. So if I do direct substitution with my x value of concern, in this case x equals 2, into my original, I'd be getting 2 squared is 4 minus 2 all over 0, so I'm getting 0 over 0. So my initial substitution results in an indeterminate form. If I have an indeterminate form, it means I can't tell what the value of the limit is or isn't simply by looking at the expression. We've got some work to do. However, because this 0 over 0, right, is my indeterminate form, we've seen that more often than not the overall limit does exist. We just have to figure out what it is. And so what tool might you want to use in order to rewrite this expression algebraically, right? What technique did you use? Kobe? Factoring, thanks. So we'll go ahead and factor that the trinomial into a product of two binomials and try again. Go ahead and tell the class what you had for your factors. So what did you have for your factors, Jake?
X minus 2 and x plus 1.
Awesome. And this is the key. We must use our limit notation throughout, okay? Because the fact that we're evaluating a limit and are not concerned with what the value of the expression is or isn't at x equals 2, I'm allowed to divide out those factors. And the reason I can do that is because a limit is not concerned with x equaling 2. It's just concerned with x approaching 2. So we must write that limit notation here. Because that x doesn't equal 2 in this limit evaluation, I can do my favorite game. Yes, that's right. The cancel game, and cancel out those factors and continue on. Now, for the first time, my x value of concern, x equals 2. Is it in the domain of my expression? Certainly, and so we can evaluate through direct substitution. Finish it out. For the first time, I can also drop the LIM. I don't have to write the limit here when I perform the direct substitution, and I get 3. Raise your hand if you also had 3. So who already had 3? Yes. Annika?
What's the other side of the equal?
On the other side of the equals would be this entire thing.
Okay.
And so that would be there. We would not say the limit as x approaches 2 equals 3. The limit is an operator. It acts upon something just like we write the sine of theta or the sine of pi over 6, right? We can't, it's a sin to write sine without an input. We don't write sin equals 1/2. We write sin of, right, pi over 6 equals 1/2. Just like we write the limit of some expression, right, as x approaches something equals 3. It wouldn't be okay to write LIM equals 2, right? That's not all right. LIM, the limit is an operator. It doesn't exist without an input. Excellent question. Great. Let's take a look at the second one. Initial substitution, right? For this one results in 0 over 4 plus 6 minus 10. I get 0 over 0. So we've got an indeterminate form, right? We've got an indeterminate form. We can't tell what the value of this limit is or isn't simply by looking at the expression, so we've got some work to do. So what would be some techniques we could employ to try and rewrite this expression algebraically? Anna?
Get rid of the absolute value bars, and then we can also factor.
Excellent. So we're going to go ahead and break it up. We're going to rewrite those absolute value bars. Rewrite the expression without the absolute value bars, and we'll try factoring that quadratic trinomial on bottom and product of binomial like before. So let's go ahead and do that. Thank you for including your limit expression, and keep in mind that we can get rid of the bars by considering the sign of the quantity inside the bars. In order to do that, we're thinking about x approaching 2, but from the left-hand side. Those are numbers like 1.9, 1.99, 1.995. As x approaches 2, but from the left-hand side, that will guarantee the quantity inside the bars will be positive or negative. Negative. Do absolute value bars return the same or the opposite of negative quantities? The opposite. That's how absolute value works. If the quantity inside an absolute value bars is positive, absolute value bars will spit out the same thing. Absolute value of 27 is 27, the same thing. But if my quantity inside the bars is negative, right, like absolute value of negative 30, then my bars will return the opposite of that quantity. The opposite of negative 30 is positive 30, and that's how absolute value always returns a positive. In this case, the quantity inside was negative, therefore, the absolute value bars must spit out the opposite of the quantity inside. And we'll do our factor first to fail. This time, what do we get for our factor? Michaela?
X minus 2 and x plus 5.
X minus 2 and x plus 5. Awesome, thank you. Raise your hand if you had the same factorization. Same factorization. Good job. Now we can go ahead and evaluate. Because we're evaluating a limit, x does not equal 2. I'm going to try and smush that just a little bit. Because we're evaluating a limit and x does not equal 2, I can now play my favorite game, this cancel game, and rewrite the limit expression. So we're well left with the limit as x approaches 2 from the left-hand side of negative 1 over the quantity x plus 5. Now is my x value of concern in the domain of my rewritten expression, Annika?
Yes.
Yes, so I can evaluate through direct substitution. I can drop the limit. I don't have to write LIM any longer, and I'll get negative 1 over 2 plus 5. And I get negative 1/7. Raise your hand if you already had negative 1/7. Negative 1/7? Woohoo! Good job, you guys. Thanks. So we already employed some techniques, right? So Anna told us about rewriting without the absolute value bars. About without. Yeah, without absolute value bars. We also did factoring. Kobe had his factor. Go ahead and tell the class some other strategies that might be useful when we're algebraically evaluating limits without the use of a calculator. So what else could we try, Savannah?
Rewriting without square root.
Good. And so how do we get rid of a square root? What was our technique there? So we rewrote it without the square root. What enabled us to do that?
We multiplied the numerator and the denominator by the square root and then the opposite of whatever function was attached.
Excellent. Yeah, same terms but opposite operation. That's called the conjugate. So we multiply by the conjugate. Thank you, Savannah. What's something else that we did? Right, what's something else that we did? Allie?
Find a common denominator.
Thank you. So we found a common denominator. When dealing with the addition or subtraction of fractions, we needed a common denominator, and that was useful as well. And we can throw in other assorted algebraic techniques. I mean, we could try expanding. We did factor out a negative in that case, and so basically all our algebraic techniques in our full bag. Algebra. Right, algebra. Awesome. Anything else that we could add to this? So you're feeling pretty good with the techniques? Your OTL number 2 was just a collection of algebraic techniques, and so I'm hopeful that went well. Thank you for paying attention to detail and being precise in your mathematical notation. You must include 4 points, the limit notation on your Unit 2 test until you perform that final direct substitution. So if you drop the limit notation prematurely, you'll lose notation points on each of those questions. You want to make sure that you don't miss out on those easy points. So you want to use the proper notation throughout. Let's go ahead and take care of that OTL number 2 now, and then we'll get going with our shortened class period. So at this time, I'd ask that you take out your OTL number 2, it was easiest to complete that on a separate piece of paper because there wasn't a lot of space there. If you complete it on a separate piece of paper and have more than one, please take a minute and staple those together. Okay, so there's a stapler on that side activity table. There's also a stapler on this front table. Please staple multiple pages together. Make sure that your heading is on top, name, 2A, and number 2 clearly labeled on top of your OTL. Give yourself credit for those who complete out of 12. Divide, enter, multiply 2, and let's box that into the canvas score on top, nice and big, round to the nearest top. Please make sure you're boxing that so it's easy to find. Marissa. Pásamelos, por favor. Keep them in the same column, front rows, if you make sure they're facing the same direction. I really appreciate that. It makes it easier to record and then get back to the very next class grade. And so, names on top, yep. Awesome.
That little staple never got to leave, so right.
Thank you. Thank you. Thank you. Go with number 2 if you did it. OTL number 2. Thank you, ladies and gentlemen, for your help grading those each and every day. I appreciate it. So today we've got a rip-roaring day as we continue our discussion with limits. We're going to move on and apply our new limit notation to a calculus definition for continuity. So we need to be able to comfortably write and understand what a limit is using correct notation in order to get our calculus definition for continuity. We already have a good understanding of what continuity is intuitively, right, and how to describe that maybe to your classmate for a continuous function or a continuous graph. Today we're going to pin down now the calculus that goes along with continuity. But first, let's take a closer look at limits involving infinity. We can evaluate limits involving infinity without a calculator by either using our knowledge of function behavior or by considering numerical values. So what I'd like for you to do is find your note sheet and take a look at a couple of these that I've picked out. Let's consider the limit of 1 over x as x approaches infinity. So we're going to kind of think about this analytically, and we'll think about it graphically, but we're not going to use a calculator. If x gets larger and larger and larger, and the top of my fraction remains fixed at a constant, in this case 1, what's the overall value of the fraction doing? Well, 1 over 1,000, 1 over 10,000, 1 million, 1 billion. What's happening to the overall value of the fraction? It's shrinking. And so as x goes to infinity, 1 over x goes to 0. And we need to know that because that will be useful throughout the year. This limit does exist and it equals 0. Graphically, you can think about the hyperbola 1 over x. Oh, that's the worst graph of all recent memory. I'm sorry I exposed you to it. Okay, my bad. Suppose that we were looking at a hyperbola as x goes to the far right side of the graph as x approaches infinity. What are my y values doing? They're getting closer and closer to y equals 0. Yes, the limit exists because there's a particular y value that the function values are approaching as you look to the far end of the graph. As x goes to negative infinity, again, it doesn't matter that my denominator is becoming more and more negative. It's becoming more and more negative without bound. The overall value of that fraction then is still shrinking towards 0. It's just going towards 0 on the negative side. So this still equals 0 and exists. What about the limit as x approaches 0 from the left-hand side? Graphically, no problem. You can see graphically as x goes to 0 from the left-hand side, we put equals negative infinity to describe exactly the manner in which it doesn't exist. But I want you to know in general, if I'm getting a 1 or a constant over 0, right, that's my indication that it's an infinite, that it does not exist. However, to determine whether it's positive infinity versus negative infinity, you can do what we call a sign test. We can think about the sign of my numerator and the sign of my denominator as x approaches that particular x value, but from whatever side it is, to determine whether it's going to be the positive infinity or the negative infinity. So once again, constant over 0 means infinite. To determine which infinity, either positive or negative, without a graph or without a calculator, you can do a sign test. Let's consider the sign of the numerator. As x approaches 0 from the left-hand side, the numerator is fixed at 1. That's a positive value. As x approaches 0 from the left-hand side, the denominator is going to 0, but it's doing so from the left-hand side, which means my denominator will be what sign? Negative. Overall, positive divided by negative is what? Negative, which is my indication that this is negative infinity analytically without a graph. Does that match our picture? Of course it does. Consider the values of my numerator. My numerator as x approaches 0 from the right-hand side. My numerator was fixed at the constant 1. That's always positive. Over, this will be infinity, right? Constant over 0 is infinite. The question is which infinity? Analytically, I could consider that by determining the sign of numerator and denominator. The denominator is approaching 0, but from the right-hand side, that's slightly positive. So positive divided by positive overall is positive. That's my analytic evaluation that this is positive infinity. You see? So you can do it with or without a graph, right? If you're comfortable with function behavior, that's great, but you might not have such a nice function like 1 over x. Yes? So the sign test can be very useful. In fact, we'll use it a lot, right, when we get into our graphical behavior using calculus. Consider the limit as x approaches 2 from the left-hand side. Okay, so we're going to try not to do this graphically. We're going to try to do this analytically. As x approaches 2 from the left-hand side, direct substitution would yield 1 over 2 minus 2 is 0. Is this an indeterminate form? No, this is not indeterminate. 0 over 0 would be indeterminate. There's nothing indeterminate about this. In fact, I can determine that that limit does not exist. It is infinite. The question is it positive infinity or negative infinity? That's what we need to determine. So a constant over 0 is infinite. It's not indeterminate, it's infinite. It's going to shoot off to one of the infinities. To determine that, we need to consider the sign of that denominator and do a sign test to determine whether it's positive or negative. The numerator, as x approaches 2 from the left, is fixed at a positive constant. That will always be positive. As x approaches 2 from the left, that's numbers like 1.9, 1.99, 1.99863, ensuring that the sign of the denominator will be slightly negative, right? 1.999999 minus 2 is slightly negative. Overall, positive divided by negative is negative infinity. And so I'm getting negative infinity for my limit evaluation. Do the same thing. I know that this is going to be infinite because 1 over 0 is infinite, but the sign of the top is positive. The sign of the bottom, as x approaches 2 from the right-hand side, is slightly positive. 2.001 minus 2 is slightly positive. In this case, a positive divided by a positive indicates that while infinite, this will be the positive infinity. And that's very different. I'm approaching the same x value, but depending upon which side I'm coming from, our y values are vastly different, right? Complete opposites. All right. What about as x approaches infinity? Well, again, graphically, we could take a look at the picture here, but if we're trying to do this analytically without looking at our graph or thinking about function behavior, instead, we could think about values as x goes to infinity. Does subtracting off 2 from an infinitely large number do much to your fraction? No, this subtraction of 2 is insignificant as x gets infinitely large. Therefore, this behaves the same as 1 over x does in our first slide, right? This is an infinite value on bottom. So this is constant over infinity is shrinking towards 0 again. Good job. Does subtracting 2 from a negative infinitely large number do much? No, and so this is also going to 0, albeit from the negative side. This is fun. I like analytical evaluation of limits. Okay, consider now an exponential expression, 2 to the x. As x goes to infinity, can we reason out what's happening to my value of the expression? Certainly, and we could do this either numerically, or we could do this using our knowledge of function behavior and thinking in terms of its graph. Well, 2 to the x is an exponential. As x gets larger and larger, 2 to the 10th, 2 to the 100th, 2 to the 1000th, my y values are ballooning towards infinity. And so while this limit does not exist, because infinity is not a particular number, a particular y value, we say that this limit equals infinity to describe exactly the manner in which it doesn't exist. Recall, as x approaches infinity or negative infinity, we're talking about end behavior, and clearly the right side end behavior of an exponential function with positive base b, right, is positive infinity. That shoots off like that. You're looking at this part of the graph. Same is true for e to the x. We know that that function also shoots towards positive infinity as x looks to the far end. So this is also infinity. As x goes to negative infinity, right? As x goes to negative infinity, that's this side. We know that we have a horizontal asymptote for our exponential function. And so if we're thinking graphically for these, we're going to try to do a better axis this time, Meg. Oh, gosh darn it. There, I'll cover it up. I'll disguise it. Our exponential functions level off. There's a shelf. There's a horizontal asymptote. Our particular y value that my function values are approaching as I look to the far left end of the graph for positive base b exponentials. So I would say what? 0. So this equals 0. And then e to the negative x. Pesky little bugger. How does that change things up? Using your knowledge of function behavior, e to the negative x is replacing my input x with the opposite of x in general for transformations. We know that causes a flip in my graph, a reflection. But it's not a reflection about the x-axis. Right? It's not a top-bottom reflection the way that replacing y with negative y is. How does this change the graph, Riley?
This is a reflection of the y-axis.
Good. So a reflection over the y-axis. Let's see if we can't do a flip. How about a flip left-right? So there's our e to the negative x. As x approaches infinity, what does e to the negative x do? Goes towards 0 as well. Awesome. What about this last one analytically? Without looking at the graph. So if we cover up the graph, could we reason this out? Well, certainly. This would be like e to the negative 1,000, e to the negative 1 million, e to the negative $1 billion. Right? That's the same as 1 over e to the positive 1 billion. That's 1 over an infinitely large number. That's shrinking to 0 like our very first slide. And so we could reason this out analytically. We could also use our knowledge of function behavior, but in each case we're doing it without a calculator and without graph and calculator technology. Nice job, you guys. All right, let's determine the given limit analytically, and we could verify graphically or numerically. So recall, right, all of your things from pre-calculus and function behavior still hold true. In fact, are necessary precursors for our discussions down in calculus. If x is approaching infinity, we're talking end behavior, right? And oftentimes we can determine the end behavior of a more complicated function by considering an end behavior model. Recall that for rational functions, an end behavior model can be gained by considering the dominant term on top over the dominant term on bottom. We saw in our activity how that end behavior model for the oblique asymptote, right, could be determined by considering the top degree divided by the bottom degree. It looked like the x was raised to one higher exponent, right, on the top over the bottom, and so it looked like we ended up getting a linear function for my end behavior, which was an indication that we had an oblique asymptote or slant asymptote. Let's go ahead and consider the dominant term on top here. The key to end behavior models is that x is approaching positive infinity or negative infinity. X is getting infinitely large. If x gets infinitely large, the only term on top, right, that's going to influence my final end behavior is the dominant term, the highest exponent term. And so this x cubed, though would be certainly large, right, it would be certainly large, will still dwarf in comparison to this quartic term, this x to the fourth term, as long as I let x increase without bound. So too would that x squared term have no effect so long as I look far and far enough to the right on the graph. And so basically, we can grab onto the quotient of the dominant terms. Keep in mind that negatives still count though. So that negative does influence the end behavior. You saw that's very important, right? A negative x cubed is very different than a positive x cubed in terms of end behavior. And so we want to make sure that we're grabbing those dominant terms, sign included. My end behavior model for this particular function then would be given by the quotient of the dominant terms. I would be getting 3x to the fourth over negative 2x, which means this function is going to behave exactly like a negative 3 halves x cubed function would behave. And so I know that that rational function, which looks complicated, would behave exactly as a negative 3 halves x cubed function, which is much simpler, namely a cubic function. So I know what cubic functions do. Those are my disco end behavior, my down-up end behavior, right? As you look to the graph, my positive kx cubed does down, increasing, level point, change curvature, increasing throughout. This is a negative x cubed. So what happens to my end behavior? Flip. I'm still disco, but now I'm up-down disco, right? Up-down disco. And so, can we answer the original question using our end behavior model? You bet your boots we can. As x goes to infinity, what does that expression do?
Approaching infinity.
Negative infinity, that's the down. So we just say, good. As x goes to negative infinity, use my same model. As x goes to negative infinity, what does my expression do?
Positive.
Goes to positive infinity, that's my up arrow, right? That's my up arrow. Sweet. As x goes to infinity, no problem, we'll get our end behavior model. And so I've got lots of terms on top and on bottom. However, because x is approaching the infinities, we're talking about infinitely large x values or infinitely small. The only one responsible for determining the end behavior is going to be dominant over dominant, sign included. So my end behavior model, can I do end behavior model this time? That'll be fun. There, I just made up a new acronym. That's end behavior model. EBM. Oh yeah. Yeah. Goodness, does this remind you about some pre-calculus things? If the degree of the numerator polynomial is the same as the degree of the denominator polynomial, right? What feature must the graph have? A horizontal asymptote. It's given by the quotient of the coefficients on my dominant terms. And so this is just going to be y equals negative 2. My end behavior, right, of my function then, my y values must be approaching negative 2. That's it. And whether I'm looking to the far right side of the graph or the far left end of the graph, that horizontal asymptote is being approached. What happens when the degree of my denominator is more than the degree of my numerator? What? The degree of my denominator is more than the degree of my numerator. Brandon?
Then there is a horizontal asymptote at 0.
At y equals 0, absolutely. And so if the degree of my denominator function is more than the degree of my numerator function, then that's an indication that my graph has a horizontal asymptote at y equals 0. If my end behavior model is y equals 0, then what does this function do? As x goes to negative infinity? Goes to 0. That's it. As x goes to positive infinity? Goes to 0. Now there may be all kinds of squiggles in between and asymptotes, but because we're looking at x going to infinity or negative infinity, we're only concerned with the end behavior, and that's what allows us to make the end behavior model. So some textbooks and some calculus texts and some calculus teachers go into a bunch of algebraic manipulations here and dividing every single term by the greatest power of x that appears in the denominator, right? And reevaluating and breaking up into hyperbola functions 1 over x's and seeing what's left. I want you to know that you can apply, right, everything we know from end behavior models in pre-calculus and FST/pre-calc compacted to answer these limited involving infinity questions on the non-calculator portion of the AP exam. So you can just make an end behavior model. So long as you do it correctly, don't forget to grab the signs. Signs count for the dominant terms, right? If there's a negative in front of that x squared, make sure you grab it if that's the dominant term. So our summary, our analytic summary for limit involving infinity, let's go ahead and suppose that we have a constant over 0. So if we have a can I not, yeah, I want it. There we go. So let's suppose that we have a constant over a quantity approaching 0. If I have a constant over a quantity approaching 0, does this equal 0? No. Does this exist? No, it doesn't exist. However, we can describe exactly the manner in which it doesn't exist by doing what? By doing a sign test. And so this would equal either a positive or negative infinity, and we can determine that using a sign test to determine which. What? Oh, determining the sign, SIGN, positive or negative of the numerator over the denominator will determine whether it's a positive infinity or negative infinity.
Okay.
So if you get positive over negative, that's an indication overall negative.
That's what I was trying to get at, but it didn't really work out.
No problem. What if I have a constant numerator and I have a quantity approaching infinity on the denominator of my fraction? Is this indeterminate?
Yeah.
Certainly not. Right? We've seen how if my top of my fraction, my numerator is fixed at a constant value, and my denominator is approaching infinity, what happens to the overall value of the limit? 0 goes to 0. So that does exist and it equals 0. If I have a quotient where the denominator is fixed, but the numerator is approaching 0, is this indeterminate? No, this is determinate. I can see what the overall value of the fraction is doing. If the bottom of the fraction, the denominator is fixed at some constant, and the top is shrinking towards 0, the overall value of the fraction is shrinking towards 0 as well. So this does exist and equals 0. No problem there. And if I have constant, constant bottom, numerator growing towards infinity. Is this indeterminate?
No.
It's not indeterminate, it's just infinite, right? This would be a situation where my function values balloon to infinity. So we can say one of the infinities depending, now this would depend on my constant. If my constant were negative, right? And I was going to positive infinity, this would be negative infinity. So this would, again, require you to consider the signs of the numerator and the sign of the denominator to determine whether it's positive or negative infinity. Would we have to do a sign test for these? The middle one here? No, it doesn't matter which side we're approaching 0 from, graphically. If it's shrinking to 0, it's shrinking to 0. We don't need a plus or minus here at all. So we don't need a sign test for this middle one. Awesome. What questions do you guys have about our analytic evaluation? All right, we're going to get after our main objective for the day. Today we're going to determine the calculus definition for continuity. We're going to determine continuity versus discontinuity, and we're going to do it using our limit notations that we developed the past 2 days. So we're going to be precise. In fact, in order to get your stamp for number 9, you're going to have to write an equation that involves a limit in order to get your stamp for number 9. So once again, our stamped eligible items in your activity today, go ahead and put a little circle around number 4, number 8C, number 9, number 10G, and then at the end of the practice, you can get a 5th stamp in today's class, a 5th stamp. In order to get your 9 stamp, you'll need to use limits and an equation, and I wrote that on the sideboard as well. During the activity today, I'll likely turn off the smartboard to save energy, and then I'll turn it back on when we come together for our discussion. We need to be able to determine the 3 different types of discontinuity as part of our objective today. and so we will have a little discussion as well as our definition using limits. Today our class ends at 11:42, and I think that we need 10 to 15 minutes. So what I want to be doing is aiming for about a half hour, maybe about 27. We want to come back together to give us enough time for our discussion, depending upon where you are. Okay? So let's go ahead and without further ado, scoot into your cooperative learning groups and get going. Remember, when you all agree, raise your hand and I'll come to you and issue stamps to everyone at one time. Thanks for getting going right away because we got short and crunch. Michaela? No, you may use calculators, right? For your investigation, we just want to be particular with our definition using limit notation. Thank you. I'll go ahead and pause the recording now. Thank you, ladies and gentlemen. At this time, we're going to ask that you stop working on your practice. I know that you want to get it done. You'll have an opportunity to earn full credit on your stamps so long as you complete this part of your regular assignment for Belloc next time, but you need to look at your note sheet because we only have until 42, okay, until 11:42 for our shortened time today. On our note sheet, we determine the requirements for continuity. In order for a function to be continuous, we had several requirements. Firstly, the function had to exist at my x value of concern. In other words, f of c exists. Secondly, we needed the overall limit of my function as x approached c to exist. That is, the left-hand limit had to match the right-hand limit in order for the function to be continuous. And we saw that in our non-examples, right, in the beginning of our 2-4 activity. And what had to be true about the overall limit and the value of the function? Well, that was our 9 stamp. Riley?
They had to be equal.
Certainly. And so we can sum up. We can sum up the overall limit existing and the function value existing, right? And then the overall limit of the function being equivalent to the function value. We can sum up our continuity requirement really in this third block. This assumes now that the overall limit as x approaches c of my function exists. It assumes that my function exists because they're equal, and then they have to be the same y value. That's our calculus definition of continuity and an equation involving the limit. That was our 9 stamp. We've got 3 different types of discontinuities, and so we've got what we call a step discontinuity. That's synonymous with a jump discontinuity. And so on your note sheet, let's go ahead and draw a nice little step discontinuity. We could say, oh, maybe my function is moving along and zoop. The only way to trace this function as I move along its domain from left to right is it to pick up my pen or pencil tip and jump up to the next level or down to the next level in order to continue my tracing from left to right. A step discontinuity is non-removable. There's no way to remove that discontinuity simply by redefining the function at one point. It doesn't matter if this was an open circle and this was a closed circle, there'd still be a step discontinuity there. That's the difference between a step discontinuity, a non-removable discontinuity, and a removable discontinuity. I could fix the problem if I were to simply redefine the function at a single point. I could in effect plug the hole, plug the open circle. And so this is when the overall limit exists, but the overall limit doesn't equal the function value at x equals c. So that picture of that can look like this. Right? The overall limit exists as x approaches c. In other words, the left-hand limit matches the right-hand limit. But what's the problem here? Well, the function value in this case doesn't exist, so it doesn't equal. Even if I had the function value up here, right, that would still be discontinuous because now the function exists, but it's not equal to the overall limit. However, we could remove this discontinuity if we were to redefine the function in a single point. Wouldn't that fix the problem? That's why it's called removable. So I could have a point there or not a point there. Still be a removable discontinuity. And lastly, an infinite discontinuity. That's synonymous with vertical asymptote. So that means exactly the same thing. An infinite discontinuity is a vertical asymptote. That is to say, as x gets closer and closer to c, from one side, the function value shoots off to positive infinity or towards negative infinity. It may be the same, right? The function values may approach positive infinity on both sides. They may be opposite, as we've seen a lot with our rational functions, right? But an infinite discontinuity is synonymous with a vertical asymptote. So graphically, we could show that. A vertical asymptote is an infinite discontinuity. Is an infinite discontinuity removable or non-removable? Could we fix that discontinuity by redefining the function at a single point? No, we couldn't. No, we couldn't. That's non-removable. So in terms of limits, the only discontinuity that's removable is the one where the overall limit exists. Right? Where the overall limit exists, that's the only one that's removable. We can still get our full stamp on our continuity discontinuity practice questions, but you'll have to complete that and then show me during bell work next class. You can still get full credit. So let's go ahead and complete our closure then, and then it'll be perfect time. F is continuous at x equals c if my function exists my overall limit exists and the third and most important requirement, go ahead and tell the class when I call on you. What's our third and most important requirement? What's our last one? Savannah?
The limit as x approaches c of f of x equals f of c.
Absolutely. The overall limit of f of x as x approaches c must be equal to the value the function takes on at x equals c, namely f of c. And that was our 9 stamp. Okay, go ahead and complete that last one then with your partner. And be ready to share letter B with the whole class. Yeah, so which part of the requirement was not met, and it could be subject, right? So on this one, the function exists. I know it because there's a break here. So at x equals -1, we're fine with this one. Right, it exists. But I need to check out other requirement there by considering the left hand and the right hand, so I can already get the overall limit. So if you just ask for overall limit, you need to check left hand and right hand.
Do like what we do, like
Yes. So the overall limit doesn't exist.
wait, we can tell the overall limit as
Because the left hand and the right hand.
okay, I thought we had to do way more.
Okay, ladies and gentlemen,
I was gonna ask more, like, is that what we have to do?
may I have your attention, please? Thank you. Let's go ahead and close our discussion today. So go ahead and share your response with B. Take a look at your partner. Raise your hand if you guys have the same thing in your blanks. Who has the same blank fill-ins? Oh, that's great news. Okay, so what can we do to complete our letter B? Allie and Annika?
It has an infinite discontinuity
On infinite discontinuity at x equals -4. Raise your hand if you got the same as Allie and Annika. Same things. Way to go, you guys. Have a great day, ladies and gentlemen. Come by if you have questions or concerns. Nice job.